In the previous video, we started to discuss an application of the Poisson distribution. We evaluated the limit as n goes to infinity of 1 minus lambda over n to the power n minus k, and we found out that the limit is e to the negative lambda, where we used the L'Hopital's rule. Consider now n Bernoulli trials. So the trials are independent. Each trial results either in a success or a failure. The probability of success is labeled as p, and then 1 minus p is the probability of failure. Define x to be the number of successes in n trials. Then x has a binomial distribution. X has a binomial distribution with parameters n and p. So the PMF of x is given by n choose k is given by p of x equals to k is equal to n choose k p to the k 1 minus p to the n minus k, and the possible values of k are 0 up to n. So let's start with the PMF of the binomial distribution with parameters n and p. And so this is the PMF of the binomial distribution. In the second line, what I did is I expressed the binomial coefficient n choose k in terms of the factorial, and in the third line here I expanded n factorial. So n factorial is the same as n times n minus 1 times n minus 2 dot 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 n minus at some point you're going to get n minus k, and the previous factor will be 1 more than that, n minus k plus 1, so I wrote n minus k factorial at the end. And so then you can see that I can cancel out n minus k factorial. Once I do that, what I obtain is n times n minus 1 times n minus 2 times dot 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 n minus k plus 1 over k factorial p to the k 1 minus p to the n minus k. So we rewrote the PMF of the binomial distribution in this way. So at this point, what I'm going to do is I'm going to take lambda to be n minus p, n times p, and then p will be lambda divided by n. So I'm going to make that substitution now, and if I make that substitution now, what I get is n times n minus 1 times n minus 2 dot 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 n minus k plus 1 over k factorial. P is lambda over n, so I get lambda over n to the k, and 1 minus lambda over n to the n minus k. Okay, so here's what I'm going to do at this point. This will be equal to n times n minus 1 times n minus 2 dot 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 n minus k plus 1 divided by k factorial lambda to the k over n to the power k times 1 minus lambda over n to the power n minus k. Now we are going to switch the k factorial and n to the k in the denominator. So well, let's just write one more line. So I get n times n minus 1, n minus 2, dot dot dot, n minus k plus 1 divided by n to the k times lambda to the k over k factorial 1 minus lambda over n to the n minus k. Now notice, look at this fraction here, and the numerator has k factors and the denominator has k factors of n. So I can write this as n divided by n times n minus 1 over n times n minus 2 over n dot 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 n minus k plus 1 can be written as n minus k minus 1 divided by n times 1 minus lambda over n to the n minus k. I'm going to write lambda to the k over k factorial at the end. Notice n over n is 1, n minus 1 over n, it could be written as n divided by n, which is 1, minus 1 over n. N minus 2 over n, that's the same as n over n, which is 1, minus 2 over n, dot dot dot, 1 minus k minus 1 over n, 1 minus lambda over n to the n minus k, lambda to the k over k factorial. So far what we have obtained is the following. N choose k. We started with n choose k, p to the k times 1 minus p to the k, n minus k. That's the PMF of the binomial distribution evaluated at k, and what we obtained that this is equal to 1 minus 1 over n, 1 minus 2 over n, dot dot dot, 1 minus k minus 1 over n times 1 minus lambda over n to the n minus k times lambda to the k over k factorial. Now what I want to do is I want to take the limit as n goes to infinity, but we have to be careful because if we change n, we might be changing lambda. So what I want to do is I want to take the limit as n goes to infinity, but in a specific way. So what is that? So what I'm going to do here is say that is the following. I'm going to assume that n is large and p is small, so that n times p remains the same lambda. So lambda, I want lambda to be fixed. So how am I going to do that? Well, look at the hyperbola of the equation n times p equals to lambda. So lambda is fixed, and so notice that in order to keep n times p to be equal to fixed lambda, while I let n to go to infinity, what I have to do is I have to take a p small accordingly. So let n go to infinity, and so that and at the same time allow let p to decrease accordingly, so that n times p is always lambda. Okay, so if I do that, then what happens? So let's come back to this expression. As n goes to infinity, notice that 1 over n, 2 over n, k minus 1 over n, they all go to 0. So as n goes to infinity, each of these factors here approaches 1. And we know that this guy has limit e to the negative lambda as n goes to infinity from the previous video, and this factor does not depend on n, so it stays the same as n goes to infinity. So finally we could say the following, that so assuming that n is big and p is small accordingly, so that n times p is fixed lambda, what we could say now is that n choose k, p to the k, 1 minus p to the n minus k is going to be approximately what I get when I take the limit of this side as n goes to infinity, and that is going to be e to the minus lambda, lambda to the k over k factorial. And notice that this is the PMF of the Poisson distribution. So once again, the right hand side here has limit e to the negative lambda times lambda to the k over k factorial, since each of the factors from here to here has limit 1. This guy has limit e to the negative lambda from the previous video. So what we have obtained is that when n is large and p is small, the Poisson distribution can be used to approximate the PMF of the Poisson distribution can be used to approximate the PMF of the binomial distribution. Okay, so let me recap. So what we are saying is that the Poisson distribution with parameter lambda can be used to approximate the binomial distribution with parameters n and p, where n times p is lambda, n is large, and p is small, so that lambda is of moderate size. As a rule of thumb, use this approximation when n is at least 20 and p is smaller than 0.05. Okay, so in the next video we will do an example where we are going to use this approximation.